Okay, good afternoon, everyone. Welcome to this session of invited talks of ICM. My name is Tong Yang from City University of Hong Kong. It is my great honor to chair this session. The speaker for this session is Professor Charlie Smart from Yale University. Professor Smart is a world-leading expert in partial differential equations and probability, in particular about the study on the particle models from statistical physics and their scaling limits. He has made fundamental contribution to the study on the interaction between smooth microscopic behavior and discrete stochastic process. The title of Professor Smart's talk today is Unique Continuation of Lattice Schrodinger Operators. Let's welcome Professor Smart. Professor Smart, you can share your PPT and start. Thank you.
Great. Thank you very much. It's a great honor to have been invited to speak at the 2022 ICM. So, thank you to the organizing committee. So that's right. So I'm going to talk about unique continuation for Schrodinger operators. So let me share my screen here.
Professor Smart, we don't see your screen, the share screen. Okay, good.
Something, how is this even possible? Okay. All right. I believe that I am now talking about unique continuation for latticing, a subject that I've been thinking about. So what I'm going to do is I'm going to study this. And then, so my motivation for studying Anderson model. Okay, so I want to start just on the Anderson model. Okay, for those of you who don't already know about it. Okay, so the Anderson model. This is a model for say electron transport in a disordered medium. Okay, so the idea is maybe you have some crystal, and you introduce some random impurities into that crystal. Okay, and you ask, what's the sort of electrical behavior? Right? So how you're asking, how do the random defects in the crystal change the electrical properties of the material? Okay, so this is really some kind of quantum mechanical model. But instead of thinking in terms of quantum mechanics, I want to just talk about kind of a classical naive version that is essentially equivalent. Okay, and that is to think about an infinite mass spring system. Okay, so the idea is we're going to take a lattice like a ZD. Okay, and we're going to put a point mass at every vertex of the lattice. Identical point mass at every vertex. Okay, and we're going to give each of these point masses 1 degree of freedom, so that a configuration is just a function from the vertices of the lattice into the reals. Okay, and now we're going to put a dynamics on the system by adding springs. Okay, so we're going to connect the nearest neighbors, so that, the point masses on nearest neighbors in the lattice with identical ideal springs. Okay? And then we're also going to connect each point mass, we're going to sort of anchor it to 0, okay, using another ideal spring, but these won't necessarily be identical, so we're going to allow the anchoring springs to depend on, we're going to allow the strength of the anchoring springs to depend on which vertex you're at. Okay, so somehow more formally, we're going to be interested in solutions to certain differential equations, possible times. from the non-negative reals into little L2 of CD, so little L2 of CD being our configuration space. And we're going to look at solutions of U double prime equals the Laplacian of U minus the potential times U. Okay, and so here, right, the Laplacian, this triangle, right, this is giving us the nearest neighbor interaction. And then, so this is the nearest neighbor interaction, and then the potential, okay, is giving us the anchoring spring interaction. Okay, so now the question is, what are the long-term dynamics of this system? This is what we want to understand. So of course, right, if the anchoring springs were all 0, okay, then this would just be like a wave equation, right? Some kind of discrete version of the wave equation, okay? But because maybe the anchoring springs aren't 0, right? Somehow the dynamics are changed, right? And the question is, how do the dynamics depend on the potential? Okay, so what we're actually going to be interested in is, where does the energy go? So there's a natural energy associated to the system. It's just, and it's local. Okay. Oh my gosh. Okay, so I see there's something in the chat. My internet is really not doing well. Okay, so I'm going to stop my video and hopefully things will improve. Okay. All right. So so there's a local energy, which is just the sum of the kinetic and potential energies at each vertex. Okay, and then the sum, so the total energy, right? So if you just integrate the local energy over the whole lattice, this is conserved, okay, by the dynamics. And so now the question is, where does that local energy go, okay, in the long time limit? So there's a classical theorem about this. Okay, this is the Rage Theorem. So the Rage Theorem says that you can take the space of initial configurations and you can write it as a orthogonal sum of two closed subspaces, say HC and HP. Okay, so that, well, if you start in HC, then the energy disperses. Okay, and on the other hand, if you start in HP, then the energy remains trapped. Okay, so here, like HC and HP, so the C stands for continuous and P stands for point. So this is really coming from the spectral theorem. Okay, and so what's going to happen is, okay, so if you start in HP, then for any epsilon, there's a radius r. Okay, so that no more than an epsilon fraction of the energy ever escapes the ball of radius r. And on the other hand, if you start in HC, then for any radius r, if you look at sort of the average amount of energy in the ball of radius r, sort of over long times, then that becomes arbitrarily small, okay, as the time goes to infinity. Okay, so maybe the cartoon version of this is the following. So like you have your initial data, say U0, and you can project that initial data into the two subspaces. Okay, so you can write your initial data as a sum. So you can write U0 as a sum of U0P and U0C. Okay, and then when you turn on the time dynamics, okay, well, the part in HP is, its energy sort of remains trapped in some bounded region for all time. Okay, whereas the UC, the part that's in HC, its energy essentially spreads out over the whole lattice. Okay, and so its energy, if you want, is dispersing off to infinity. Okay, so this is a very, very general theorem, okay, that applies to more than just the Anderson model. Okay, but so now the question is, okay, so we have this nice orthogonal decomposition, and we want to understand sort of how do these spaces HC and HP depend on the anchoring springs, right? How do they depend on the potential? Okay, so here are kind of the most basic theorems along these lines. Okay, so first of all, so when V is periodic, so when the potential is periodic, there's a theorem of Thomas that says that HP is always 0. Okay, which is to say, the energy always disperses when the potential is periodic. Okay, so the Thomas theorem is really for the continuum. Okay, although the proof, his proof works also in the periodic lattice case. Although, okay, for the lattice, you can get away with some kind of easier Fourier analytic proof if you want. Okay, but you want to think, just by Fourier analysis, okay, the energy always disperses, okay, when the potential is periodic. Okay, on the other hand, when the potential is random, something very different happens. Okay, so here by random, what I mean is I want to choose say, pick a beta that's positive, and then my potential is going to be independent, uniform, random field where each, the value at each vertex lies in the interval 0 beta. Right? So like v of x is a uniform random variable on the closed interval 0 beta, and then of course all the value at all of the sites, those values are independent. Okay, so if we have this sort of sufficiently random potential like this, then again, so the behavior is very different. So first of all, in dimension 1, okay, by spectral averaging, it turns out that HC is always 0. Okay, so that is to say, the energy is always trapped. Okay, so this is the sort of exact opposite of what happens in the periodic case. Okay, so in the periodic case, if you have a periodic potential, okay, if you start, say, with some compactly supported initial data, okay, the energy eventually sort of spreads over the whole lattice and in some sense escapes to infinity. Okay, but at least in dimension 1, if the potential is random, okay, then the energy essentially stays trapped in a compact region for all time. Okay, so somehow like the waves are bouncing off of the random defects and are being reflected back towards where they started. Okay, and so the energy stays trapped. Okay, so in higher dimensions, the picture is a little bit more complicated. Is this? Gosh, okay, hopefully, it looks like my internet is still being unstable. Okay, I think, was there just a 10-second lag? Okay, I'm just gonna continue. Okay, all right, so, right, okay, so it's a little bit more complicated in higher dimensions. Okay, so what we know mathematically, okay, is that this is either by multi-scale analysis or the fractional moment method. What we know mathematically is that, well, HP is not 0, okay, as long as beta is positive. So in the random case, there's always some trapping, okay? So there's some trapped states. There's some initial, there are some initial data for which the energy stays trapped in a bounded region for all time. Okay, on the other hand, and we also know that if the noise is large enough, okay, so if beta is sort of sufficiently large depending on dimension, okay, then HC is 0, so sort of all of the energy remains trapped. And this is really somehow because on the lattice, the Laplacian is bounded, okay? And so the noise can sort of eventually dominate the diffusion. Okay, so that all of the energy always gets reflected back towards where you started. Okay, so this result, the sort of math in the higher dimensional case, is not completely resolved, and in particular, we don't really understand what happens when the noise is small in high dimensions. Okay, and this is the subject of kind of the two most important conjectures. Okay, so what are the important conjectures? Okay, so first of all, in dimension 2, okay, so dimension 2 should be like dimension 1. Okay, so in dimension 2, if the noise is at all non-trivial, okay, so if beta is positive, then HC should always be 0, almost surely. Okay. On the other hand, in dimensions 3 and higher, when the noise is small, okay, HC should actually be non-zero almost surely. So that is to say, like in high dimensions with small noise, both HP and HC should be non-zero almost surely. So there are going to be some trapped states and some dispersive states, okay? And it's really sort of how this conjecture that that Anderson won the Nobel Prize for. Right? This is telling us that if you take a crystal in 3D and you introduce some random defects, but not too many, okay, then you end up with a semiconductor, okay, because some low energy electrons are trapped, but high energy ones can move. Okay, so I'm going to put in here a sort of a third conjecture. So even though this is less important than the first two, okay, so what is the third conjecture? The third conjecture is that really this phenomena is supposed to be universal. Okay, so in particular, it's not really supposed to depend on the structure of the noise. So instead of uniform random variables, we should be able to put any kind of randomness that we want. Okay, we should be able to put any kind of law that we want for the random variables, provided that it's non-trivial. Okay, so in particular, all of these, the previous theorems and the conjectures, they really ought to be true, say, for Bernoulli noise. Okay, so let's say the potential takes its values in the set 0 beta, okay, and takes each value with probability 1/2, okay, independently at random. So these previous results really ought to be true for for singular noise, in addition to the nice continuous noise. Okay, so this is sort of my motivation. I'm trying to make progress on these conjectures. Very slow plotting progress. And okay, so I want to somehow tie this back to unique continuation. Okay, so how am I going to do that? Well, so let's think for a second about how you actually solve the wave equation. Okay, so so if I want to solve u double prime equals Laplacian u minus potential u, okay, well, one way to do that is to observe that well, the right hand side is linear. Okay, in fact, it's even better than that. It's a nice self-adjoint operator. Okay, on the right hand side, and so we have this nice self-adjoint operator. So in particular, the spectral theorem applies. So it's bounded self-adjoint operator. So we have the spectral theorem. So we can just essentially write out a basis for the operator. Okay, and then just read off the possible solutions. Okay. Okay, so we're in infinite dimensions, so the spectral theorem is more complicated. Okay, so the spectrum is going to split into different pieces. So there's going to be some eigenvalues maybe, and also some continuous spectra. Okay, and when we have eigenvalues, that's going to tell us that HP is non-zero, and when we have continuous spectrum, that's going to tell us that HC is not zero. Okay, but the point is somehow, at least formally, okay, if you want to understand whether or not HP is non-zero, whether or not HC is non-zero, what you can do is you just look at solutions of the eigenfunction equation. Okay, so HC equals lambda C, and you ask yourself, what are the possible rates of decay at infinity for these for solutions? Okay, and if it's possible to decay rapidly so that you're in L2, okay, then well, then you're going to have point spectrum. Okay, on the other hand, if it's not possible to decay that quickly, okay, then you're going to have continuous spectrum. Okay, so so if you want, sort of at least formally, understanding the possible rates of decay for solutions of the eigenfunction equation at infinity, tells you whether or not you have localization or delocalization. Okay, so I claim that you can, at least formally, this is a question about unique continuation at infinity. All right, so let me try to continuation. We learned function, and it is identically 0 on a non-empty open set. Okay, then it actually has to be identically 0 everywhere, right? So this is a classical theorem. We learn about the 2D case in complex analysis, and then the same proof works in all dimensions. Okay, provided you started with the correct proof in 2D. Okay, so fine. So this is a classical result, and I want to consider sort of a reasonable generalization of this, which is so what happens to unique continuation when instead of looking at RD with the flat metric, okay, we put on some other Riemannian metric. Okay, so that is to say, I want to try to understand what happens to unique continuation when we put when we instead study the divergence form elliptic equation div A grad. Okay, so we have a solution of div A grad u equals 0. Okay, where A is some measurable uniformly elliptic coefficients. Okay, so like this, the A here is supposed to be some matrix valued measurable field, and it's supposed to be symmetric. Okay, and its eigenvalues are supposed to be bounded below and above by some positive constants. Okay, so we look at div A grad instead. So this is the Laplacian with respect to a measurable metric. Okay, and we like to understand whether or not we have unique continuation. Okay, and it turns out that the answer to this depends on the regularity of the coefficients. Okay, so if the coefficients are Lipschitz continuous, then, well, there's a theorem of Hormander that tells us that we have unique continuation. Okay, so if the solution vanishes identically in some non-empty open set, then it has to vanish identically everywhere. Okay, on the other hand, if the coefficients are not Lipschitz continuous, okay, like say they're only Holder continuous, so they're C alpha for some alpha between 0 and 1, then unique continuation can fail. Okay, so how does this work? Well, this really only works in dimensions 3 and higher. This is this example, and the basic idea is you're going to build kind of a solution by laminating together sort of faster and faster oscillating harmonic functions. So you look at the harmonic function, which is sort of a cosine in one direction and exponential in another. So you have these cosine exponential functions, and what you do is, okay, so the cosine exponential, that's going to be harmonic provided that the frequencies match. Okay, and what you do is you start to glue these together, and you oscillate sort of faster and faster. Okay, as you glue these layers together, and the faster oscillations allow you to decay more rapidly. So you're sort of, if you want, so you're gluing these layers together, oscillating faster and faster, and you're using the coefficients. Okay, you have to construct the coefficients that allows you to sort of glue these layers together and still be a solution. So you glue these layers together, oscillating faster and faster, and the layers can get smaller and smaller. And in the end, you can essentially you become 0. Okay, so the solution actually vanishes. Okay, on a half space. It's non-zero and vanishes on a half space. And this is possible because, again, the coefficients are Holder continuous and not Lipschitz. So somehow the lack of regularity allows you to build a solution with this kind of fractal structure. Okay, so why am I talking about measurable coefficients? So the reason is so the Laplacian on the lattice, the lattice Laplacian. Well, this is a discrete version of the continuum Laplacian. Okay, so in a lot of ways, it really behaves like the continuum Laplacian. Okay, but in other ways, the Laplacian on the lattice really behaves like like a periodic divergence form operator with measurable ingredients. So, I'm going to claim that in a lot of ways, the Laplacian on the lattice is really analogous to div A grad, okay, where A is measurable, okay, and periodic. Okay, that maybe this is a better analogy than the Laplacian for what's happening with the discrete Laplacian. Because unique continuation is subtle, that maybe unique continuation is also subtle for the Laplacian on the lattice. Okay, and okay, there are some kind of interesting subtleties. So what's happening on the lattice is, okay, so unique continuation fails, okay, in general. Okay, but there are certain situations in which you can recover some kind of unique continuation. Okay, so I want to think first about sort of two cases. Okay, so let's say we have, a solution of the eigenfunction equation on the lattice ZD. Okay, so if, for example, we knew that that eigenfunction actually vanished, say, on sort of two consecutive, axis-aligned layers. So, like, if I have this solution C and a solution of the eigenfunction equation C, and it, vanishes on the set x1 equals 0 and x1 equals 1. So if it vanishes on these two layers, okay, then it turns out that the solution has to vanish identically. Okay, so why? Well, so let's look at this 2D cartoon. Okay, so we vanish on these two slices, and then if we look at the equation here, say at this point in one of the slices, okay, so what does the actual equation say? Well, it's some linear equation in the value at this site and the neighbors. Okay, but now something important happens, which is that the neighbors, okay, all appear with coefficient 1, okay, in that relation because of the Laplacian, right? They only appear in the Laplacian, and they have the coefficient 1. Okay, and moreover, there's only one neighbor that's outside of the two layers. Okay, so all of the values inside are 0, and there's only one outside and has coefficient 1. Okay, and the relation is linear. Okay, and therefore, the equation at the site in one of the two layers tells you that the neighbor outside also has to be 0. Okay, and so now if we repeat this, if we look at the equation at all of the vertices in, say, one of the layers, it tells us that all of the adjacent vertices have to also be 0. Okay, and so now by induction, C has to actually vanish on the whole lattice. Okay, on the other hand, if we don't have axis-aligned layers, then this breaks down. Okay, so for example, let's say we take diagonal layers instead. Okay, so so if we have diagonal layers, it turns out that even if you know the values on two consecutive diagonal layers, there are going to be infinitely many ways to extend that to a solution on the whole space. Okay, and in fact, so you can actually choose the values, say, on some ray departing from the diagonal layers, some sort of axis-aligned ray departing from the layers. You can pick whatever values you want along that ray, and then that's going to determine the solution. So there's going to be, a unique solution that says 0 on a diagonal half space and equal to some prescribed function on an axis-aligned ray going in the other direction. Okay, going away from the diagonal half space where the function vanishes. Okay, and you can just again prove this by induction. You just use the equation to sort of solve for the diagonal layers. Okay, one after another. Okay, you can just construct the whole solution this way. Okay, so unique continuation on the lattice can be a bit subtle. Okay, because sometimes it works and sometimes it doesn't. Okay. All right, so you might complain, okay, with this example that this isn't really a failure of unique continuation, and so how could this not actually be a failure of unique continuation? Well, we haven't really controlled the growth okay, of C when in this half space. Okay, so maybe it's possible somehow that fine, there are infinitely many extensions, but they all grow doubly exponentially, and so there's unique continuation, say, in the class of slowly growing functions. Okay. However, this is not the case because there are some nice examples where the growth is under control. Okay, so there's a family of examples. This is Judomirskaya that work in any even dimension. Okay, and so here, let me just talk about what happens in 2D. Okay, so in 2D, if you think about the function which just alternates plus or minus 1 on a diagonal line and is 0 outside, so I claim that this is an eigenfunction of the Laplacian. Okay, so this is sort of easy to check, right? The Laplacian is just is sort of 0 far away from this diagonal line. That's easy to see. Okay, if I'm adjacent to the diagonal line, then the Laplacian is also 0. Okay, because of the sign alternation. Okay, and of course, and the function is 0. So we definitely solve the eigenfunction equation off of the diagonal line, and then on each diagonal line, well, you can just compute, right? The Laplacian at a +1 site is -4, and the Laplacian at a -1 site is 4. Okay, and so we have an eigenfunction of the Laplacian. Okay, that's supported on a diagonal line, and is bounded. Okay, and now there's a standard trick for converting this into a harmonic function in one dimension higher. Okay, where we just pad, so we add an extra variable, and then we multiply by an appropriate exponential factor. Okay, where the exponent just depends on the dimension. Okay, and this makes the function harmonic. Okay, so in particular, in odd dimensions, okay, there's going to be, so in dimension 2D plus 1, there's a harmonic function, okay, that's supported on a subspace of codimension D, okay, and grows at most exponentially. Okay, so there are these kind of difficult examples, these examples that show that unique continuation really fails in a strong way. Okay, so nonetheless, we can actually use unique continuation to prove some interesting results. Okay, so first of all, so we can use unique continuation, say to prove the Thomas theorem. Okay, for periodic potentials. Okay, so how does this go? Okay, so let's suppose for contradiction that we have some periodic. We have a periodic potential, okay? And we have a solution of the eigenfunction equation that's in L2. Okay. So somehow there's no avoiding the Fourier analysis, but we can make the dependence a little bit softer. Okay, so there's an amazing theorem of Couchment that sort of works for very general periodic operators, which sort of tells us that if there's an eigenfunction in L2 of a periodic operator, okay, then in fact there's another solution of the eigenfunction equation that, in addition to being in L2, actually decays super exponentially fast. Okay, and if we take the super exponentially fast decaying function and we combine it with our sort of layer by layer unique continuation result, okay, we can arrive at a contradiction. So the basic idea, okay, is that we have this super exponentially decaying function, okay. And if we look at sort of two consecutive layers kind of far out at infinity, okay, and now we apply our layer by layer unique continuation result, okay, what happens is the layer by layer unique continuation result, sort of as you go from layer to layer, the size grows by at most a constant factor, okay? So you have sort of at most exponential growth from the layer to layer unique continuation. But on the other hand, you have super exponential decay as you go out to infinity, okay? And so if you combine these, what you see is that, if you're trying to understand how large the function is on some slice near the origin, okay, if you choose your layers arbitrarily far out, okay, you can see by unique continuation that the function has to be arbitrarily small on any slice, okay? And so in this way, you see that there can't be any L2 eigenfunctions, okay, for periodic potentials. And this is by a unique continuation from infinity. Okay, so of course, we're using a very, very weak form of unique continuation here. And really, somehow, a lot of the heavy lifting is done by this Fourier analysis, right? The fact that the operator is periodic allows us to get super exponential decay. And the super exponential decay is sort of strong enough that we can get away with a very weak unique continuation result from infinity. Okay, so if we say wanted to make progress for random potentials, we would need stronger unique continuation results. Okay, and there's been a lot of kind of partial progress along these lines. Okay, so just kind of just returning briefly to the classical continuum case. Okay, so there's a classical result which tells us that if we have a solution, say of of Laplace u minus potential u equals lambda u on the continuum, so on RD, okay, and the potential decays rapidly at infinity, so it decays faster than 1 over the radius, okay, then by Carlin estimates, you can prove the following kind of energy inequality. You can prove, say, that the energy in any R ball of u is bounded by some constant times the energy in the annulus surrounding that R ball. Okay. And okay, so the key point of this estimate is that this constant out in front here does not depend on the radius. Okay. And so what this tells us is that if u is non-zero, okay, then at least a constant fraction worth of the mass is always outside of any ball. Okay, so in particular, the sort of total L2 mass has to be infinite. Okay, in this situation. So the situation where the potential decays. Now there's an analogous result for the lattice, okay, which you can prove just using resolvent estimates. Okay, and in fact, there's kind of an amazing improvement that you can deduce from a paper of Bourgain. So Bourgain has a paper from 2004 where he studies Laplace plus a random potential where the potential decays at infinity. Okay, and what Bourgain can prove is that we actually have an inequality like this. Well, okay, Bourgain actually proves something much stronger, and you can deduce this inequality from what he proves. So he proves that we have this inequality even if the potential only decays like 1 over the square root of the radius. Okay, provided that the potential is random. Okay, so when the potential is random and decays, you have resolvent estimates that you need to get this kind of inequality. And so in particular, there are going to be no L2 solutions of the eigenfunction equation. Okay, when you decay like 1 over the square root. Okay, so this is kind of partial progress on improving unique continuation at infinity. So now I want to transition in the last 7 minutes, I guess, to talking about sort of quantitative unique continuation results. Okay, so quantitative unique continuation results. So these are also useful in studying the Anderson model, and in particular, so this was introduced by Bourgain and Koenig. So it turns out that if you want to make progress on this third conjecture from before, where you're trying to handle singular noise, okay, one sort of tool in order to try to understand this case is quantitative unique continuation. Okay, so there's there's this nice theorem that Bourgain and Koenig proved, which says essentially if you have a continuum solution of Laplace plus a potential, okay, on RD, then it can't decay too rapidly at infinity. Okay, that it sort of decays at most like e to the minus radius to the 4/3 power. Okay, and they used this along with a multiscale analysis in order to study the continuum Anderson-Bernoulli model. Okay, and since I'm interested in the lattice Anderson-Bernoulli model, okay, I wanted a discrete analog of this. Okay, so to get this, so I was stuck on this for a long time, and the sort of breakthrough for me came from a paper by Buchowski, Lugunov, Molinikova, and Sodin. Okay, so these authors proved kind of an amazing unique continuation result, an amazing Louisville theorem on Z2. Okay, so we all know the Louisville theorem for the Laplacian, which says that if you have a bounded harmonic function, then it's constant. Okay, and what these authors can prove is that on Z2 you actually have a much stronger result. Okay, and I'll say in a moment why it's much stronger. So if you have a harmonic function on Z2 that's bounded, say, 95% of the time, okay, so it's like bounded on a 1 minus epsilon fraction of the sites asymptotically, then it's constant. Okay, so that is to say you can sort of tolerate a defect, say, of density epsilon, and you still have the Louisville theorem. So this is much stronger because, well, it turns out it's false on Z3 by the Jittermeier-Skaya example from before, and on R2 because there are harmonic functions that vanish outside of a strip. Because this is a result which is very special to the two-dimensional lattice. Okay, and so this has a nice corollary. It tells us, for example, answered a question of Levine and Perez that there are no sort of interesting stationary random harmonic functions on Z2. Okay, so answered this interesting question. And for me, what was even more interesting about it was half of the proof of this theorem was a quantitative unique continuation statement. Okay, which said that if you have a harmonic function in a square, okay, then it is at most sort of exponentially. If you look at the so if you have a harmonic function in a square, okay, and say it has a modulus 1 at the origin, okay, then well, it's at most exponentially small in the side length on a positive density set of vertices in the square. Okay, so this is a quantitative unique continuation result, and so what Jean-Ting and I did was we kind of took this result and we figured out how to prove a sort of a random analog of this. So of course, this quantitative unique continuation result is going to fail for deterministic potentials. Okay, again because of this Jittermeier-Skaya example. Okay, but it turns out that if the potential is random, then you can recover a version of it. Okay, that works with high probability. Okay. There's a downside, though, which is, of course, so it only works with some probability. And then the density, okay, it doesn't actually have full density. You only get support on some fraction of the sites that depends on the side length. Okay, so the density goes like 1 over the square root of the side length. Okay. Okay, but it turns out that this is sufficient, along with the Bourgain-Koenig multiscale analysis, to prove localization for the Anderson-Bernoulli model. So I'm going very quickly because I only have 2 minutes left. Okay, so right. So there's a kind of a nice follow-up by Lee. Sort of a few, noticing some additional structure in the problem, he can sort of get rid of the sort of density of support. And he used this to study large disorder for the Bernoulli-Anderson model. Okay, so again, I guess I have 1 minute, so now let me just kind of summarize. Okay, so there's another follow-up by Li and Zhang, where in 3D, okay, they can prove a deterministic unique continuation result, okay, where again, the density depends on the side length. Okay, but this this also suffices to prove localization. Okay, and so finally, let me just end by mentioning some open problems. Okay, so these unique continuation results sort of leave So there's a lot missing from the picture. So we kind of understand what's happening in 2 and 3D, although the 3D result maybe is weaker than it should be. Okay, so I want to make some conjectures. Okay, so what I conjecture is that this, this Li-Jiang result should hold in any dimension less than or equal to 7. Okay, but should be false in dimensions greater than or equal to 8. Okay, and then the analog of the random Lie result, that's strengthening of my theorem with Ding, this really ought to be true in all dimensions. Okay, all right. Well, I guess I'm out of time. So thank you very much.
Thank you, Professor Mark, for the excellent talk. So I guess we don't have enough time for questions. So thank you again.